Hello again, Math 20-1s. In today's lesson, we're going to continue to look at geometric series, albeit this time we're going to focus more on different types of word problems, specifically ones that deal with geometric growth and geometric decay. You can find this lesson on page 53 of your Math 20-1 work booklet. So let's jump right into this first example. The Globe and Mail published an article in 2010 stating that the University of Victoria is struggling with an out-of-control rabbit population. Yeah, we also have that same problem in the neighborhood I live in. At the time of writing in January 2010, there were an estimated 1,500 rabbits on the University of Victoria's grounds. If the rabbit population increases at a rate of 20% per year, complete the table below, giving an estimate of the rabbit population in January of 2011, 2012, and 2013. We're actually going to do B first, because B is going to make it a bit easier to actually do these calculations. We do know, though, that we're starting with a rabbit population of 1,500. For B, to show that the sequence representing the rabbit population is geometric and state the common ratio. Well, we're just going to calculate the common ratio based on the information that's given here. Okay, so to calculate the common ratio, we're first going to calculate it as a percentage. So the common ratio would be 100%. Now, the 100% represents the present value of the rabbits. But what we also need to do is we need to add this growth percentage number, the 20%. So we're going to add 20%. So this is my growth percentage. If you do this, you would then get a common ratio of 120%, which means that every year the population is going to increase by 120%. So it'll be 100% of whatever it is to start the year off, plus an additional 20% of growth. However, we don't write down the common ratio as a percentage, so we're just going to convert that to a decimal number by dividing the number here by 100. And as a decimal number, that would be 1.2. There's no real reason to write down the 0 after the 2 because it's a trailing 0 after a decimal. Now that we know the common ratio, we can actually calculate what the rabbit population in these following years would be. So all you do is you simply just take this number and just start multiplying by 1.2. So if you multiply this by 1.2, then it would give you 1,800. And if you multiply this number by 1.2, you would get 2,160. And if you multiply this by 1.2, you would get 2,592. So I've represented this rabbit population growth as a geometric sequence. C, if term 1 in the geometric sequence is the number of rabbits in 2010, which term of the sequence represents the number of rabbits in 2025? So when you first look at this, you might be like, okay, to subtract the years, so 2025 minus 2010, and that would represent, I think, term 15, but you have to be a bit careful with this, okay? So we're going to have to count this properly. So here's the deal. I'm going to start by counting off. So when n is equal to 1, that is 2010. Now, I want to know what the n value is when I get to 2025. So we can go ahead and we can count this. Okay, I'll use like a little tally chart to keep track of what I'm doing here. So this would be 2010, 2011, 2012, 2013, 2014, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So actually, in 2025, we're going to be in year 16 that we're actually interested in. So just got to be a little bit careful when you're given these, given a population in terms of like years, then you want to like relate that to the number of terms that are going to be in the sequence. If the population continues to grow at this rate, estimate the rabbit population at the University of Victoria in January of 2025. All right, so we just clarified that in 2025, you're dealing with n is equal to 16. And what we want to calculate is we want to calculate what the value of term 16 is. So T16 would be a question mark. We know that the starting population of rabbits in the year 2010 is 1,500. And we know the common ratio is 1.2. I'm going to use my general formula for a geometric sequence to determine this value. So we'd have Tn is equal to a r to the power of n minus 1. So in January 2025, we're in year 16. So it's going to be T16 would then be 1,500 multiplied by r, which is 1.2, raise this to the power of 16 minus 1. And then you'd have T16. You can just plug that into your calculator in one shot. The only thing to be careful about is just make sure that when you put the 16 minus 1 into the exponent, either make sure your calculator puts it in as a superscript, and if it doesn't, just make sure it's in brackets there. Otherwise, it'll raise to the power of 16 and then subtract 1 as if the 1 isn't in the exponent at all. What this would give you is you would then get 2, 3, 1, 1, 0.5. Okay, but the thing is, you have to make like real, make physical sense out of this. Like you can't have 0.5 of a rabbit. So actually, in this situation right here, we're going to round down because we want to know how many like whole rabbits we actually have. You can't round up because you actually don't have that number of rabbits. So we're going to round down. And then we would get term 16, which is the rabbit population in 2025, would be 23110. And the note it makes right here is it says we're in this situation we're dealing with geometric growth factor. So the geometric growth factor is the value of the common ratio in a pattern exhibiting geometric growth. And in this example, the geometric growth factor is just the value of the common ratio, which is 1.2. Now we're going to look at a situation where we have something decaying. So as like years pass, like whatever our term values are in the sequence, they're going to start to progressively get smaller and smaller. Second example, Vinny borrows $10,000 from his parents to buy a car. His parents lent him the money interest-free as long as he makes a payment at the end of every single year. That's nice of them. They agree on a repayment scheme, which results in Vinny owing 10% less at the end of a particular year than the beginning of the year. This repayment scheme lasts for 8 years. At the end of 8 years, he makes one final payment to pay off the loan. Okay, so we want to complete the table to show the amount he owes at the end of the first 4 years. Okay, so at the end of year 1, well, we're going to need to calculate that in, actually, I think in a moment here. Well, I think at the end of the year, then he has to like actually make a bit of a payment. So at the end of year 1, like he would owe $10,000. Okay, now to determine the remaining values here, we're going to again do part B first, just to determine what the common ratio is. So in this situation, R would be equal to 100%. Now, this time around, it says that he owes 10% less at the end of a particular year. So we're going to subtract 10%. Okay, so in this situation, once again, the 100% is like the present value. And we're subtracting this time around because we have a percent decay. If we calculate this, this would be 90%. And if we convert it to a decimal number, we're going to get 0.90. I just want to make a quick note about what you're considering or what you're thinking about anytime you deal with decay. So I'm just going to make a little note here. So in decay, I'd always ask yourself, what percentage is retained for R? So here, we would not write down R as 0.10. That's how much we're removing. The amount retained would be 100%, subtract the amount that's removed, the 10%, so your R value would be 0.90. So to fill in the amount that's owed at the end of the first 4 years, so we're going to take this one and multiply by 0.90. So that would just be 9,000. And then get term 3 by multiplying again by 0.90. This would be 8,100. And again, multiply by 0.90. And this would give you 7,290. C, state the geometric growth factor. Well, we did that. Okay, the geometric growth factor would be 0.90. The value of the common ratio. D, how much does he owe at the end of year 7? Okay, so year 7 would be when n is equal to 7. So again, this would just be n equals 1, n equals 2, n equals 3, n equals 4. And we want to know what the value of T7 is. We know the amount owed at the end of year 1 is 10,000. Again, he makes a payment at the start, I think, of the year. Okay, and then R would be 0.90. Going to the general formula for a geometric sequence, you'd have T of n is equal to A R to the power of n minus 1. We want to calculate T7, which would be 10,000 multiplied by R, which is 0.90. If your R value is between 0 and 1, it's going to make the term value start to go down. If the R value is bigger than 1, it's going to make it go up like it did in the previous example. So this would be 0.90, 7 minus 1. And again, if you want, you can plug that into your calculator in one step. Just make sure you place some brackets and follow the order of operations. This would end up giving you, we're going to round to the nearest cent. So this would be $5,314.41. So I believe at the end of year 7, that's when they have to make a lump sum payment. Yeah, it lasts for like 8 years. It makes the note here. Yeah, if the growth factor is between 0 and 1, we're dealing with geometric decay. If it's bigger than 1, then we'd be dealing with geometric growth. Third example, we're going to do some quick calculations to determine what the R value are in various situations. So A says the rate of inflation is increasing by 3.5% per year. So that would be R is equal to 100% plus 3.5%. So that would be 103.5%. Divide by 100, and then you get 1.035. So that's the growth factor or the common ratio. B, the number of fish in a lake is decreasing by 2% each year. So again, when you're looking at the R value, you're asking yourself how much is retained. So the amount that would be retained would be 100% minus 2%, which should be 98%. And then if you convert that into a decimal number by dividing by 100, it'd be 0.98. So 98% is retained every single year. C, the number of rabbits is in a population is doubling every single year. If you see the word doubling, we just take 100%, we just multiply by 2. So in this situation, it would just be R is 2 multiplied by 100%. So R would be 200%. Convert that to a decimal, I suppose. Divide by 100. That'd be R is equal to 2. So that's a growth factor of 2, which means we're doubling. The value of a computer decreases by 1/5 every single year. So this would be R. It's actually easier to do this calculation as a decimal calculation instead of worrying about percentage. So 1/5 would be equal to 0.2. So what we have right here is we take the present value as a decimal, which is 1, and then subtract the amount that the computer value is decreasing by. If you convert that fraction, it'd be 0.2. And then this would be 1 minus 0.2 would just be 0.8. And again, in geometric decay, you're asking yourself for the R value, what amount is retained. So if the value of the computer is decreasing by 1/5 or 20%, the amount of value retained would then be 100% minus 20%, which is 80%. E, the ball rebounds to 3/4 of its previous height after every single bounce. This actually flat out tells you what the growth factor is. So again, you're trying to ask yourself, like, what amount is retained. So if you had, like, for example, a ball that was like dropped from a height of like 1 meter, okay, so it like falls down and then it bounces back up, and it bounces back up to 3/4 of the original height. Sorry, that should be a 4 there. Yeah, the height retained would actually be 3/4. So if you start with 1 meter, it'd be 3/4 of that. So your R value in this situation would actually just be 3/4. And if you convert that into a decimal, it'd be 0.75. Okay, you want to think about it like this. You can say like the amount of height retained. If it said the ball lost 1/4 of its height, then you would go 1, subtract 1/4 to get 3/4. But it's already telling you what's retained in the first place. So there's no need to go ahead and do that. But let's deal with this ball type situation because these ones are actually a little bit tricky to deal with. A rubber ball is dropped from the top of a 20-meter building. Each time the ball bounces, it bounces back to 80% of its previous height. Okay, so this is the amount of height that's retained. So immediately that's going to give me an R value that's 0.8. If you convert that into a decimal, 0.80 or 0.8. Calculate to the nearest centimeter the height of the ball after the 15th bounce. Okay, now we're going to solve this problem using 2 different strategies, and it's going to have to do with like the n value again and how it like properly matches up with the term number. So the first student decides to solve the problem using a geometric sequence with t1 is equal to 20. Now it says explain why the value of T15 does not give the answer to this problem. Well, here's the thing. T1 is equal to 20 meters. That would be the height of the ball before it even bounces. I'll say height of ball. I'll say before being dropped. So that would be 0 bounces. If you looked at T2, T2 would then be the height after 1 bounce. Okay, so you got a bit of a problem right here because the term number and the number of bounces are not properly matching up. So if we were to look at T15 here, T15 would be the height after, you got to subtract 1. So it would actually be the height after 14 bounces. So again, the term number is not matching up with the number of bounces. So we have to account for that when using their strategy. Okay, so it says solve the problem using, I'm not sure to say the student's name, Lucacito's method. Okay, so we want the height after 15 bounces. So 15 bounces, if we're going to use this method right here, we would actually need to increase the term value by 1. So what we're looking for is we'd actually be wanting T16. Because again, T1 is the height before there's even been 1 bounce. So T16 would be the height after 15 bounces. Okay, so you'd have n is equal to 16. Okay, so let's use our general formula for a geometric sequence. You have T of n is equal to a r to the power of n minus 1. And we want to calculate T16. This would be equal to a, which is 20 meters. So a here is 20 meters. Multiplied by r, which is 0.8. And then to the power of 16 minus 1. And then again, you can go ahead and plug that into your calculator if you'd like to confirm it. If you do plug it in, we're going to round it to the nearest hundredth of, it wants the nearest centimeter, so we're going to go the nearest hundredth of a meter and then convert it. So that would be 0.70 meters. And if you convert that, that would be T16 is equal to 70 centimeters. Now, that's one way to do it, but again, it's kind of confusing just because the bounce number and the term number are not perfectly matching up. The second student's going to use a method where we do a bit of a correction in advance so that they actually do match up properly. So Nicolette wants the value of T15 to be the solution to the problem. We want T15 to represent the height after 15 bounces. Now, it says explain why the first term in Nicolette's sequence does not equal to 20. Okay, well, just think of it like this. So she wants T15, which is N15, to be the height after 15 bounces. So in her sequence, if we match things up like this and we go back to T1, so T1, where n equals 1, would be the height after one bounce. The height after one bounce is not 20. Okay, 20 is the release height. So you release it, then it bounces to like a new height. So we actually need to calculate what that number is going to be. So that's actually really easy to do, to calculate what her first term in the sequence would be. So A is equal to T1. Well, all you do is you take the original height, which is 20, and then you just multiply by the growth factor, which would be 0.80. So in her sequence, 20 times 0.8 would be 16. In her sequence, that would be the height after the first bounce. Okay, now we can go ahead and we can solve this. So solve it using her method. So we want to calculate T15, which is a question mark, when n is 15. The first term in her sequence is 16 meters, and the geometric growth factor is 0.8. So use the general term formula. T of n is equal to a r to the n minus 1. And we want to calculate T15. So this would be equal to 16. So again, that's the height after the first bounce. It's retained 80% of its original height. Multiply by r, which is 0.8. And then we're going to go 15 minus 1. And it's going to give you the exact same answer as above. So this would be 0.70 meters. And if you convert that into centimeters by multiplying by 100, not T16, T15, you'd have T15 is equal to 70 centimeters. So again, just got to be really careful with like how you try to set up the problem. Either approach works. I mean, if you don't want to change the first term value, then you're going to have the bounce number and the term number offset by 1. If you want to calculate what the height is after the first bounce, then the term number and the number of bounces would actually properly match up. I would probably do method B because I don't like it when things don't match up like that, but it's your call in terms of how you prefer to solve it. Unless, of course, the problem tells you to solve it in a specific way like it does here. C, for each student, write an equation which represents the height of the ball after X bounces. Okay, so let's go to the first student. Lucacito. So his equation, if we write down a general term formula, so general term formula would be T of n is equal to a r to the n minus 1. So this would be Tn is equal to 20 multiplied by 0.8 n minus 1. Now it says instead of using n for the number of bounces, we're going to use x. So I'm just going to replace the n's here with x's. We'll write down tx would then be equal to 20 and then 0.8 x minus 1. Okay, so that's their equation. For Nicolette, do the same thing. We'll get a general term equation. So we'd have T of n is equal to, her first term is 16. So you'd have 16. And then you'd have 0.8. Actually, we got to correct this. This is wrong here. I made a mistake with Lucacito's. Okay, 16 times 0.8. And then we've got x minus 1. And I'll explain to you why it's wrong in a second here. Okay, so you have to remember again that for Lucacitos, the bounce number is actually equal to, the bounce number is actually, it's like if we go back up here again, the bounce number is always one less than like what the term number is. So the bounce number would actually be n minus 1. So that'd be x is n minus 1. So here we actually we're not going to write down x minus 1 here because n minus 1 is x. Okay. The bounce number is the term number, subtract 1. So we're just going to erase this here. Again, this is why I really don't like the method where the bounce number and the term number are offset, because it does get a little more confusing. But hopefully that makes a bit of sense. Okay. So yeah, it says x bounces. And again, the bounce number is the term number minus 1 in Lucacito's sequence. Sequence. D, write an equation which could be solved to determine the minimum number of bounces required for the rebound height to be less than 2 centimeters. Okay, we're not going to worry about the less than part just right now. Let's just say that we want to write an equation that identifies how many bounces is required to have a rebound height of 2 centimeters. So that would be when t of x has a value of 2 centimeters. So depending on who you want to actually use here, and again, we got to convert this, by the way, because the original equation's in meters. So that'd be 0.02 meters. So if we use Lucacito's equation, all we're going to do is we're going to replace t of x with 0.02. So your equation would be 0.02 would be equal to 20, and then 0.8 multiplied by x. And Nicolette, we're going to again replace, I forgot to change that to a tx here. My bad. Let's quickly flip that. So tx is going to be 0.02. And then 16. And then we're going to have 0.8. And then x minus 1. So those are two equations we could use to solve the bounce number for 2 centimeters. And like I said, we'll deal with the less than in just a moment. All right, use the intersect feature on a graphing calculator to determine to the nearest tenth the minimum number of bounces required for the rebound height to be less than 2 centimeters. It doesn't actually matter which equation you use right here. If you plot both equations, they're going to look identical. So let's use the equation that has a little bit less in the exponent. So we'll use Lucacito's equation. So for Lucacito's equation, what I'm going to do is I'm going to plot y1 is equal to 0.02 in my calculator. So I'll plot the left-hand side of the equation. And then y2, I'll plot the right-hand side of the equation. So it's going to be the 20. And then the 0.8x. And then we're going to use the intersect feature. Okay, so let's go to the calculator now and actually plot this. So this would be y. We're going to clear this. We're going to clear this. We got 0.02. And then the second equation, we're going to plot down 20 multiplied by 0.8. And we're going to raise that to the power of x. And let's go ahead and graph this. Okay, let's go to Zoom Standard first and see what happens. If we can actually see anything. No, not quite. Now, just remember right here, the first equation would be a horizontal line that pretty much passes through the y-axis at 0.02. So that's this blue line. Like it's pretty much along the y-axis. Now I need to see an intersection point, which is definitely going to be over towards the right. So I need to make the x maximum bigger. So I'll go to window. Let's change the x max to 20. Now remember, the x represents a number of bounces. I mean, this problem's probably done after 20 bounces anyway. So let's go ahead and graph it. Oh, not quite. Okay. So let's make it a little bit bigger. Let's do like maybe 30. The one equation might have a horizontal asymptote, so we're not quite seeing when it intersects. Yeah. Maybe we should zoom in a little bit on this area so we can properly see the intersection point. We don't need all this empty space beneath the x-axis. So we'll change that to window, and then let's just make the y max 0. Actually, make it -1 because it's so close to the y-axis. Actually, we'll make it even smaller. Let's go window. Let's make the y max 1. And actually, I'm going to make the y minimum a little bit less than the x-axis, just because I need to be able to see the intersection point a bit more clearly. I want to be able to see the x-axis. Okay, it's still fine. It's still a little bit difficult to actually see what's going on. Oh, I changed x. I think that was my problem here. No, it's fine. Okay, let's change this to 0. Go ahead and graph this. Let's just try to calculate it right now and see what actually happens here. Maybe 30 is still not quite enough. Let's make this a bit bigger. Let's go to a window and let's change this to 50. Okay, yeah, now I can definitely see the red curve get beneath the blue one. So again, it's just like everything with this intersection method. It's trial and error with the window settings to actually get the intersection points. Now we can calculate it. So I can calculate, find the intersect, and it looks like it's somewhere about like right here. This is where like the red curve crosses the blue line. Hit enter and enter. Go ahead and guess the solution. And it says x is 30.9. Okay, so let's write down the solution here. Then we'll make sense of that less than thing. All right, so it is x is 30.9, I think it was, 30.96. And that occurs when y is equal to 0.02. So that's where y would be 2 centimeters. Now, it does say we want the rebound height to be less than 2 centimeters. So to be less than 2 centimeters, we'd actually have to go beyond this number. So in this situation, I'm actually going to round this 30.96 up. Okay, because if you go beyond 30.96, then immediately I'm going to be less than 2 centimeters. So this would then turn into x is equal to 31 bounces. So if you're dealing with a physical problem, you kind of have to stop and think about, like, does it make more sense to like round it up or round it down? Here we round it up because to get less than, this would actually be the number if it was exactly at 2 centimeters. So anything less than that is you'd have to go past this number, which would then be 31 bounces. All right, one more example. Mike invests $5,000 in a GIC. Each year, 3% interest is added to the value of the investment at the beginning of the year. I wish GICs still had that interest rate. I don't think they do. Consider the geometric sequence, which represents the value of the investment at the end of each year. Okay, so A, we're going to start off by stating what the growth factor is. So to do this, we'd have R is equal to 100% of the present value, and 3% interest is we're adding that amount every single year. So plus 3%. This would be 103%. And then this is going to give you, if you convert it to a decimal number, R is equal to 1.03. B, write a product which represents the value of the investment after 1 year. This product represents the first term in the sequence. Do not evaluate this product at this time. Okay, so we're going to do that correction right away. So the original value is 5,000. We want to get the value of the investment after a year. So when n equals 1, that's going to be after 1 year, not the original value. So to calculate this would be, how do you calculate the amount after 1 year? Well, you just take 50 or 5,000 and you just multiply it by 1.03. Okay, that's going to be the value of A. Okay, it wants that to be the first term in the sequence, A or T1, whatever you want to call it. Now, we're not going to calculate it right now just because the problem commands me not to do it. Now, it says write a value of write a product which represents the value of the investment after 2 years. Okay, so that would be where n is 2. So the way to do this is, yeah, I could set up the general term formula, but another way to do it is I could just simply start off the original value. If you multiply by the growth factor once, that is the value after 1 year. If you multiply by the growth factor a second time, that's going to be the value after 2 years. So that this is going to be T2. And again, it doesn't want us to evaluate the product this time for whatever reason. D says use the formula T of n, so or my general formula for a geometric sequence, to write an expression which could be used to calculate the value after 10 years. Simplify, but do not evaluate this expression. Okay, so let's see here. Value of the investment after 10 years. So this would be T10. Would be equal to well, let's identify what all the stuff is first. So here, A would be equal to 5,000 times 1.03. So this would then be, okay, so the value of A, I'm actually going to write this in red. Okay, so the value of A would be 5,000 times 1.03. Then the value of R would be 1.03. And we're going to raise this to the power of 10. Now, I can actually simplify this a little bit further, because if you look at the equation here, what I have is I have two bases. I have 1.03 and 1.03. I can actually combine the two exponents on these. So if I kind of expand it, I can show it a bit more. So this would be like 5,000 times 1.03 times 1.03 to the power of 10. This is an exponent of 1, so what you could do is you could write this as 5,000 and then 1.03. If you have common bases and you want to combine the exponents, you just add them. So we're going to go 1 plus 10. So this would then be T10 would be equal to 5,000. And then it'd be 1.03 to the power of 11. Okay, now E wants me to actually go ahead and calculate these different numbers. Okay, so what's the value of the investment after 1 year? Well, now we can just go ahead and calculate that. So let's plug that into our calculator. So that would be 5,000 times 1.03, which would be 5150. We're going to go to the nearest cent. So 5150.00. The value after 2 years would be 5,000 times 1.03 times 1.03. So this would be 5304 decimal 50. And then what's the value after 10 years? Well, we can just use this equation right here to determine it. So again, this does make sense. It should make sense anyway. So yeah, A is the value of the investment after the first year. Okay, we multiply by, we combine the exponent. Oh, did I miss a 1 here? I think I missed a 1. Yeah, my bad. Yeah, sorry, I forgot to write down the -1 up here. Yeah, there should be a -1. Whoops. Let's change that. Yeah, because T of n is a r to the n minus 1. So I forgot the -1 up there. Okay, so this would actually be 9 at the up at the top. So then this would be 1 plus 9. So this would actually be to the power of 10. Let's just double check that again. So yeah, T10 is A. A is 5,000 times 1.03 multiplied by R, which is 1.03 to the power of n, 10 minus 1. So you have 10 minus 1, which is 9. Combine the exponents and you get to the power of 10. Okay, so let's go ahead and calculate that now. So it'll be 5,000 times 1.03 to the power of 10. And this would give me a value of 6719.58. Okay, that seems right to me. Okay, use the formula Tn equals AR to the power of n to write an expression which could be used to calculate the value of the investment after n years. Show this expression can be written as a power with an exponent of n. Okay, so we're just going to do the same exercise as we did up here, except this time around, we're not going to replace n with 10. So this would be, okay, so Tn would be equal to, and again, A is the value of the investment after 1 year. So that's 5,000 times 1.03. And then multiply by the growth factor, which is 1.03. And this time, we're not going to replace n with 10. It's going to be n minus 1. Let's not forget that -1 this time. So once again, you can still simplify by combining exponents. We can write this down as 5,000 multiplied by 1.03. 1.03 would just be to the power of 1 times 1.03 to the n minus 1. Now, I can combine these exponents here. So if you combine the exponents, you just add them all together. So that'd be like going 1 plus n minus 1. And that would just cause the 1s to cancel off. So it's just be equal to n. So T of n would then be equal to 5,000 multiplied by 1.03 to the power of n. Okay, so that's my general formula for calculating the value of the investment after n years. Okay, G says suppose that the investment that an investment of P dollars earns an interest of I% per annum. Develop a formula for the amount A of the investment after n years. This formula is known as the compound interest formula. Okay, so we're just going to do some just quick replacements of variables here. So we have T of n is equal to 5,000 and then 1.03 to the power of n. Okay, A represents the value of the investment after n years. So we're actually going to replace T of n with A. P represents the starting amount of the investment. Well, that's the $5,000. That would just be P here. Now, how exactly did we calculate what 1.03 was? What we did is we had 100% plus the actual interest rate, which was I%. If we write this down as decimals, though, this would actually be 100% would just be 1. And I, we just write down as, this would then just be I as a decimal, okay? So if I do a complete substitution of the equation, you get something called a compound interest formula, which tells you that the value of your investment is equal to the starting value multiplied by the value of the growth factor, which is, or should say the value of the common ratio, which is 1 plus I, and then all to the power of n. It makes a note that the compound interest formula is an application of the general term of a geometric sequence, and then you might develop consider this topic in a bit more detail in the future math course. I feel like that might be like something you deal with again in like the logarithms unit, which I made reference to in the previous lesson. All right, so that's it for this lesson, and you can reinforce these concepts by completing on page 57. Do numbers 1, 4, 7, 8, 9, 13, and 15. So 1, 4, 7, 8, 9, 13, 15. And I'll talk to you in the next lesson.